First of all, thank you to the organizers for inviting me to this exciting conference. I've been really enjoying it. So over the past 2 days, we've learned a lot about polar climate change, and my presentation will focus on its impacts and how its impacts are not just local, but far-reaching. So essentially highlighting the importance of polar climate research. And instead of focusing on specific study, I'll be providing an overview of a number of studies that point to the far-reaching impacts of extratropical climate perturbations. Right, so to start off, it's widely accepted that the tropical perturbations can influence climates far beyond the tropics by generating planetary scale waves. For example, this recent cooling over the past several decades has been linked to Californian drought, Australian flooding, and drought in Horn of Africa. And by the way, please remember that in observations, this eastern tropical Pacific has been cooling over the past several decades. And I will get back to this later in my talk. And we've known since 1980s that how these tropical perturbations induce global scale impacts. But the reverse, how high latitude changes impact the tropics, has begun to be explored only recently. And the high latitude control for tropical circulation was first suggested by paleoclimate evidence. For example, the cold periods over Greenland were synchronized with dry and cold northern tropics and humid and warm southern tropics, suggestive of a southward tropical precipitation shift. And the so-called energetics framework provides a theoretical basis for how high latitude climate perturbations can lead to shifts in the tropical precipitation. So let's consider the case where the southern extratropics receives more energy than the northern extratropics, for example, by Antarctic ice melt or northern hemisphere aerosol cooling. Then the heli circulation needs to transport energy northward towards the hemisphere with relative energy deficit, and the energy is directed toward following the direction of the upper branch of the heli circulation. Then the moisture near the surface will be transported southward towards the hemisphere with relative energy surplus, thereby shifting the tropical precipitation southward. And the extent to which this tropical precipitation shifts in response to extratropical perturbations is proportional to the amplitude of cross-equatorial atmospheric energy transport, which is modulated by the radiative feedbacks associated with water vapor, clouds, as well as dynamic ocean adjustments. Right, so this energetic framework predicts that there will be shift in tropical precipitation in response to inter-hemispheric contrast at any given latitude. So as long as there is energy imbalance between the two hemispheres, the tropical precipitation and circulation will shift. And a number of studies then showed how tropical precipitation responds to extratropical energy perturbations. For example, the northern extratropical air pollution, northern high latitude vegetation changes, Arctic ice loss, Antarctic ice sheet melt, and stratospheric ozone hole. So all these extratropical energy perturbations have been shown to affect the tropical precipitation distribution. But then how important is this? So we asked ourselves what meridional locations are most effective at shifting the tropical precipitation. And to answer to this question, we used an aquaplanet slab ocean model. We prescribed surface cooling in the southern hemisphere and surface heating in the northern hemisphere, but at different latitudinal locations. And we ensure that the area integral of the heating is the same in all cases. And one might naturally expect that the tropical precipitation will respond more effectively to the lower latitude forcing because of its proximity. But interestingly, we found that the tropical precipitation shifts more in response to higher latitude forcing. So in other words, higher latitude forcing is more effective at shifting the tropical precipitation than lower latitude forcing. And that's because the cloud radiative feedbacks are more positive in the extratropics in this model. Right, so the high latitude forcing can shift the tropical precipitation. Then would it also have an impact on the opposite hemisphere? Would it be able to perturb the high latitudes of the opposite hemisphere? So to address that question, we again used the aquaplaning slab ocean model and prescribed surface heating in the northern extratropics, and then examined how this impacts reach the remote locations. So in response to northern extratropical heating, the helicirculation responds in a way to transport energy southward. And as a result, the southern helicirculation gets stronger, intensifying the southern subtropical jet, thereby drawing the eddy-driven extratropical jet equatorward, which then produces anomalous easterlies in the southern high latitudes. And these anomalous easterlies are accompanied by eddy momentum flux divergence. And based on QG dynamics, this will lead to anomalous northerlies in southern high latitudes, southern hemisphere. So this secondary circulation then induces downward motion in southern high latitudes, increasing the temperature through adiabatic warming. So we find from these experiments that high latitude forcing in one hemisphere can even affect the high latitudes of the opposite hemisphere. So essentially revealing a pole-to-pole teleconnection. All right, so far we've been considering the hemispherically asymmetric forcing that will lead to shifts, meridional shifts in circulation. Now here we considered hemispherically symmetric forcing. Again, we used aquaplaning slab ocean model and prescribed surface heating at different latitude locations, but in both hemispheres. Again, we ensure that the amplitude of heating is the same in all cases. The right panel shows the SST response to this surface heating at different latitudinal locations. And the polar heating turns out to be most effective at heating the globe and amplifying the polar warming. And there is a tendency for higher latitude forcing to be more effective at warming the entire globe. And this is primarily due to the lap stretch feedback. All right, so these aquaplaning slab ocean experiments indicate that the high latitude of forcing in one hemisphere can shift the tropical circulation precipitation and also have an impact all the way into the high latitudes of the opposite hemisphere. And this higher latitude forcing is more effective at shifting the tropical precipitation than lower latitude forcing. And it's also even more effective at warming the entire globe than the lower latitude forcing. So these aquaplaning slab ocean experiments really highlight the extratropical impact. But then, is this really true in a more realistic coupled climate models with dynamic ocean? So here we now use a fully coupled model and prescribe CO2 forcing only in the equatorial region or in the off-equatorial region of both hemispheres. And consistent with aquaplaning slab ocean simulations, we find that the surface warming is stronger in response to off-equatorial forcing than the equatorial forcing. Then we were wondering whether the off-equatorial forcing in different hemispheres would have a different efficiency in warming the globe. So in another study, we again used a fully coupled model, but here we prescribed CO2 forcing at 5 discrete latitudinal bands. And here's the surface temperature response over the first 20 years. And in response to equatorial CO2, the surface warming is very much muted compared to the 2 other off-equatorial forcing cases. The global mean surface warming in response to equatorial CO2 is only 10% of the other off-equatorial forcing cases. And in response to northern hemisphere off-equatorial forcing, this warming signal is more or less confined to the forcing hemisphere. And that's because the mean ITCZ is displaced northward, thereby effectively blocking the warming signal to reach the central to eastern equatorial Pacific. In contrast, the effect of the southern hemisphere off-equatorial forcing extends all the way into the eastern equatorial Pacific because the mean ITCZ is displaced northward. So the equatorial Pacific responds most strongly to the southern hemisphere of equatorial forcing and weakest to the local equatorial forcing. Right, now let's revisit the case with high latitude forcing in one hemisphere. So we've seen from slab ocean experiments that high latitude forcing in one hemisphere will induce strong cross-equatorial headley circulation response. Now the upper panel shows the response from a fully coupled model. And you can see that the cross-equatorial headley circulation response is much muted compared to the slab ocean model. So the studies around this time then suggested that maybe the extratropical impact on the tropics might have been overemphasized because of the use of slab ocean model in previous studies. But then we found that the fully coupled models actually disagree widely on how much extratropics influence the tropics. So here, they used two different models and prescribed the same southern extratropical cooling. And found that one model shows a very large tropical precipitation response, whereas the other model showed only a weak response. Then the question is, which is more realistic? Right? Is southern extratropics really going to have an impact on the tropical Pacific in reality or not? So to address the intermodal spread, we conducted a multi-model intercomparison project. Here, the control simulation, the pre-industrial one, is perturbed by reducing insolation in the southern extratropics. And we integrated these 9 fully coupled models for 150 years and analyzed the last 50 years. So please note that here we're focusing on the slow quasi-equilibrated response. Right, so here shows the multimodal mean response of SSD and precipitation in response to the southern extratropical cooling. And this southern extratropical cooling induces triangular cooling patch in the southeastern Pacific and a northward ITCZ shift. Now the right panel shows the precipitation response averaged over the eastern Pacific in individual models, and we can clearly see a large intermodal spread. And we want to understand what is controlling this intermodal spread. So in response to radiative cooling over the Southern Ocean, this cooling anomalies propagate equatorward, preferentially in the eastern basin, following the climatological southeasterlies. And as cooling anomalies reach the subtropical region, the lower tropospheric stability increases, promoting the development of stratocumulus clouds, which then reflects more solar radiation, thereby amplifying the SST cooling. And this positive stratocumulus cloud feedback is essential for exciting this Southern Ocean-driven teleconnection. So the models with stronger subtropical cloud feedback tend to show a larger northward ITCZ shift in response to the same Southern Hemisphere extratropical cooling. Now here, the black and gray lines indicate the observed estimate of the subtropical cloud feedback. And it's important to note that the majority of models really simulate too weak cloud feedback compared to observations, thereby underestimating the Southern Ocean-driven teleconnection. Right? So this suggests that the models with a strong Southern Ocean-driven teleconnection would be more realistic. All right, now the extratropical impact on the tropical Pacific is not zonally uniform, as we've already seen. So in response to the northern hemisphere extratropical cooling, this cooling anomalies only penetrate into the equatorial Pacific through the western basin because of the mean ITCZ blocking effect. And the effect of southern hemisphere extratropical cooling extends all the way into the eastern equatorial Pacific. So the northern hemisphere extratropical cooling reduces the zonal SST gradient in the tropical Pacific, whereas it increases in response to the southern hemisphere extratropical cooling. Now, these are the results from a slab ocean model. And now the upper panel shows the results from a fully coupled model averaged over these 50 years. So after a century. And you can see that now the cooling is amplified in the eastern basin, regardless of the forcing location. Right? And that's because this time scale, after 100 years, the subtropical oceanic cell has enough time to connect the subtropical waters with the eastern equatorial Pacific with upwelling waters. So, and this is consistent with an earlier study that showed El Niño-like warming in response to both Arctic and Antarctic sea ice loss. Okay. So this extratropical forcing has an impact on, or perturbs the spatial pattern of the tropical Pacific SST. So it also has an impact on the Walker circulation. Now here, these two bars are the results from the fully coupled model, and these the two bars are from the slab ocean model. And as the zonal SST gradient increases in fully coupled model, regardless of the forcing location or forcing hemisphere, the Walker circulation strengthens in both cases in the slow time scale. But as associated with this contrasting zonal SST gradient in slab ocean simulations, the Walker circulation is sensitive to the forcing hemisphere in the slab ocean model. And we may consider this slab ocean model result to represent the fast response in a fully coupled model before any ocean adjustment takes place. So in this case, with northern hemisphere extratropical cooling, which is shown in these red bars, we may expect that the Walker circulation will first weaken in the fast time scale and then transition to strengthening in the slow time scale. And this two time scale response has been confirmed from a recent study. So here they used a fully coupled model and prescribed northern hemisphere extratropical aerosol cooling. Okay. And here shows the first 3-year average response, and the right panel shows the response after a decade. And we can clearly see a two time scale response transitioning from the warming to cooling in the tropical Pacific. So in the fast time scale, this warming signal is blocked from entering the equatorial Pacific due to the mean ITCC blocking effect. And in the meantime, the Halley circulation shifts southward, which weakens the trade easterlies and reduces evaporation, thereby warming the surface in the Southeast Pacific. Now, after a decade, the subtropical oceanic cell connects the subtropical waters with the equatorial Pacific, so the cooling anomalies emerge in the equatorial Pacific. So the northern hemisphere aerosol cooling drives two time-scale tropical Pacific SST response. Now, in reality, the aerosol forcing itself has undergone a transition. So here shows the trends in aerosol optical depth before and after 1980s. And you can clearly see that the northern hemisphere aerosol emissions increased before 1980 and then declined thereafter. So the climate response to aerosol forcing at present may be a superposition of the slow response to aerosol-induced cooling prior to 1980s and the fast response to aerosol-induced heating after 1980s. Okay. Now, based on this recent study, we can see that both the slow response to aerosol cooling and the fast response to aerosol heating will contribute to driving cooling in the eastern equatorial Pacific. And now here shows the observed SST trend between this 1979 and 2013 during the historical period. And despite the evident global warming trend, the eastern tropical Pacific has been cooling. And this is one of the most pressing problems in our community because coupled historical simulations really have a hard time capturing this. And a decade ago, this discrepancy was often attributed to internal variability associated with the phase shift in PDO. However, there's now more compelling evidence that this Eastern Pacific cooling is not entirely driven by internal variability, but at least partially externally forced. First of all, this Eastern Pacific cooling has been persistent into more recent years, as we can see from observed SST trends extended to year 2024. Additionally, the multi-modal large ensemble rarely capture the observed Eastern tropical Pacific cooling. So it's likely that the observed Eastern Pacific cooling is at least partially driven by external forcing. And I've already mentioned that maybe the evolving aerosol forcing in the northern extratropics may have contributed to this Eastern Pacific cooling. And motivated by our idealized experiments in earlier studies, we also looked for the potential contribution from the observed Southern Ocean cooling. And in fact, this Southern Ocean cooling is another feature that the multi-modal large ensemble really failed to capture. So we repeated the historical simulation while restoring the Southern Ocean SST anomalies to follow the observed cooling trends. As Southern Ocean now feels the cooling trend, we were able to simulate the cooling in the southeastern Pacific, which is similar to observations, but distinct from the overall warming in the standard historical simulation. Then the question is, what is driving this Southern Ocean cooling? As Marika already showed on Monday, there are studies that suggest this observed Southern Ocean cooling is actually a response to the tropical Pacific cooling, not the other way around. I don't deny that linkage, but here I'd like to emphasize that the Southern Ocean cooling can arise independent of the tropical Pacific cooling. For example, by Antarctic meltwater, mesoscale ocean eddies, natural multi-decadal variability associated with deep ocean convection, and arguably Antarctic ozone hole. And the potential role of mesoscale ocean eddies can be seen from our kilometer scale historical simulations. Now the left panel shows the observed SST trends in the historical period, and the right panel shows our icon coupled historical simulation at the resolution of 10-kilometer atmosphere and 5-kilometer ocean. And by explicitly resolving the mesoscale ocean eddies, we were able to simulate the substantial cooling trend over the Southern Ocean and its connection into the Southeastern Pacific. And this similarity between the observation and our high-resolution historical simulation is really striking as we extend the period up to year 2024. But it's important to remember that this Southern Ocean impact on the tropics is really model-dependent. And it's actually Sally who first ran the Southern Ocean pacemaker simulation. And she actually found pretty weak Southeast Pacific cooling in her paper. And we repeated that simulation with CESM2 and found substantially larger cooling in the Southeast Pacific. And that's because CESM2 simulates a realistically strong subtropical cloud feedback, whereas it's much too weak in CSM1. So we claim that the strong Southern Ocean driven teleconnection in CSM2 is more realistic. All right, so actually there are other mechanisms that have been proposed in the literature to explain this observed Southern Ocean cooling, but here I've only proposed or showed the potential contribution from the evolving aerosol forcing and observed Southern Ocean cooling. And the research in recent years has been actually especially exciting for me because I was really able to tell that what we learned from idealized experiments had direct relevance to a pressing real-world problem. Right, so here, based on a number of studies, I've demonstrated that extratropical climate perturbations have far-reaching impacts. First of all, extratropical forcing is effective at warming the globe. And its impact on the tropical Pacific SST is not spatially uniform, so it also influences the Walker circulation strength. And the Northern Hemisphere extratropical forcing drives a 2 timescale tropical Pacific SSG response, suggesting that the evolving aerosol forcing may have contributed to the observed Eastern Pacific cooling. And I've also proposed that the observed Southern Ocean cooling may have contributed to the Eastern Pacific cooling. And due to limited time, I didn't get to introduce our most recent result. But what we found that the CO2 forcing confined to land. So here we only prescribe CO2 over land. And we found that land CO2 forcing initially cools the equatorial Pacific. So we now think that maybe the observed Eastern Pacific cooling is a result of the fast land warming, and which will transition into the El Niño-like warming as the slow response to CO2 forcing becomes more dominant. Right, this is it, but I'd like to end by advertising exciting job opportunities at MPI. Please help me spread the word, and if you're interested, please feel free to reach out. Thank you.
Hi, Sarah. Thank you for a fantastic talk. This is a really useful overview. I'm really curious about the kind of third thing you presented, the thinking about subnocean cooling. I recognize here you're looking at sea surface temperatures, but it strikes me that that region you're looking at, where you're transition from subnocean to the equatorial Pacific, that's a place of formation of Antarctic intermediate water. And so I'm curious if you've looked at like deep water connections at all to potential responses here, recognizing those are definitely working on slower timescales.
Unfortunately, no. I only look at sea surface.
Yeah.
Yeah, but
it's very cool because that's a very interesting location.
Yeah, and this pattern is actually model dependent, and we now actually think that this pattern will be sensitive to the double ITCZ bias. Here, the cooling signal in the Southeast Pacific is kind of limited south of the equator, but we think that that's because of the double ITCZ bias. So if in a model with improved bias in the tropical precipitation, we expect this to be much more triangular-like.
Yeah. Thank you.
Yeah. Thank you.
Thanks, Sarah, for the great talk. I had a question about the potential role of the aerosol forcing in driving the tropical Pacific cooling. And if you said this and I missed it, I apologize. But if that was the case, how come the climate models don't reproduce the cooling? I mean, they should have the aerosol forcing, right? Did they not have the correct aerosol forcing, or something about their response to the aerosol forcing is not correct?
Yeah, I think there are two possibilities. One is aerosol forcing itself is uncertain, so maybe it's underestimated. And actually, if we do the surface energy budget decomposition to this surface temperature response, then the cloud response is really important. And so here, the cloud feedback was also instrumental in amplifying the cooling response, and it's the same for the case with the Northern Hemisphere aerosol forcing. So the subtropical cloud feedback, underestimated subtropical cloud feedback may be also playing a role here. Yeah.
Okay, thanks.
Thank you.
If I may, thanks a lot for the talk. Couple questions. One is on this middle panel. You are saying there are 2 timescales. Are there any more? In this middle panel, you are saying that there are 2 timescales, kind of a little bit faster one, or annual, interannual, and then some kind of decadal. So are there any more timescales? Like, would you expect, I don't know, centennial, something like that?
Centennial.
Like, is it, how sure, or is there a possibility that it's just some kind of multiple spectrum or continuum spectrum in what you've seen as a response?
Maybe, but based on our dynamical understanding, I think there will be just 2 timescales. And here, in response to Northern Hemisphere extratropical forcing, actually this is not my study, my collaborators. But she finds this fast response only for the first 3 years. But then actually the timescale of the fast response depends on the forcing profile. So in our experiments where we put forcing at different latitudes, this fast timescale can extend up to like 20 years.
Okay.
Yeah.
And another question is like on kind of climate models. In the middle of your talk, you showed the result from multiple models, but my understanding they were all like 1 degree probably. And then in the very end, you showed extremely high res and the behavior is completely different. So could you comment or speculate what would be like the requirement for either model resolution or specific representation of processes that are needed to kind of simulate those processes that you're describing here?
Yeah, so I think a hierarchical modeling approach is really useful. The first model that we used, the aquaplanet simulations, I think is really useful for understanding the fundamental mechanism. But there we ignored the ocean dynamics. And then when we use the more realistic fully coupled model, and all this 2 timescale response all comes from the ocean dynamic adjustments. So, but I think we were able to understand those details after only learning those fundamentals from the aquaplanet lab simulations. Yeah. And for the high resolution, it depends. I don't think we need high resolution for all kinds of like problems. But as here, because CMIP class models really have hard time getting the Southern Ocean cooling, whereas with just one ensemble of high resolution model, we were able to really simulate extremely strong Southern Ocean cooling. So maybe for this particular problem, high resolution model is critical. Yeah.
Hi, thank you for the great talk. So in the beginning, you said using sub-ocean model, the off-tropical forcing can impact the other side of the poles. Is that right?
Yes.
And then later on, you were saying using dynamic ocean models. Is that response weakened? Or
no, there is actually pole-to-pole teleconnection, but that's actually driven by AMOC.
Oh,
yeah.
oh, okay. So the time scale is very, very long.
Yeah.
What kind of time scale is that? And then what kind of magnitude is that in terms of the...
I'm not sure about the magnitude, but it's actually not my work. Based on previous paper, they show the linkage between the northern extratropics and the southern extratropics lagged by a few decades, and they claim that's because of the AMOC. Yeah.
Okay, thank you.
Yeah.
That was very great.
Thank you.
Go ahead. Okay. Yeah, just to say thanks very much for a fantastic talk, actually. And I wanted to, well, I had a couple of questions, but I'll just ask one at a time and then take my turn. But some discussions we've been having during the coffee breaks is about sort of the next stages in model intercomparison projects focused on polar amplification. So we have MPI-M, and your work really, it's more of a comment that your work is really suggesting we should be broader in our approach, you know, that you really learn a lot as you transition forcing from the extratropics to the poles, and that seems to keep coming up over and over again. So do you have any thoughts on MPI-M in particular? I'm sure you know the protocol well, and whether we should be broadening that to, right now MPI-M is divided between CIS forcing and then global SST forcing, right? But it seems it's suggesting here that you're able to get groups of people to do other experiments. So I'm wondering what you're thinking about for the next stages of these sort of polar influence type model intercomparison projects.
It depends what your question is. If you're interested in the Arctic amplification itself, I actually think the local forcing is most important. But if you're Actually, I'm not familiar with MPI-M.
I assumed you were, so sorry about that. Yeah,
no,
so
I haven't never used it.
The experiments that are most commonly looked at are simply to change sea ice according to 2 degrees of global warming, and then see what the response is both in the Arctic but also globally.
In the fixed SST.
Both fixed and coupled SST, and that was that project has been it's about 5 years old, I guess, at this point, and responses are weak but robust, is what people are finding, and there's sensitivity to how models represent the very dynamics you're talking about, eddy mean flow interactions and so on. And now at this stage, this project is on, is thinking about a PMIP2. So, but it's really confining the forcing to the poles as one strategy. And then Yannick and others have found, sensitivity to the vertical distribution of the forcing. They can actually, can nudge the polar atmosphere to, and so there's different strategies they've been taking. But they also have global SST simulations without any change in the Arctic, and and the Antarctic forcing as well. So that's the kind of mix of simulations.
Yeah, these days I'm actually interested in this 2 timescale response, which you can only identify with ensembles. So I'm pushing for, even for above 4 times CO2 simulation, I wish we have ensembles so that we can look into the transition period. So for those PMIP type experiments, I think looking into the transition, maybe there is also transition. I think there must be a transition response. So having ensembles, would be one natural step. Yeah.
Fantastic talk. Thank you very much. I was curious about that. You showed that really high resolution run that had the amazing match in the SST trend pattern. So you explained that some of the remedy there was the mesoscale eddies in the Southern Ocean. I'm curious if the cloud feedbacks are also better in that run. And either way, I'm just curious if you could comment on, do you need both of those fixes to really get that, or is one more important than the other?
Yeah, so I think, that you actually summarized very well. So I think we need both the Southern Ocean cooling and the strong cloud feedback in order to capture this horseshoe type cooling pattern in observations. And in this particular high resolution model, the cloud feedback is pretty strong at the high end of the CMIP spread. Yeah, and then, we're still exploring why there is this Southern Ocean cooling, but we think it's the heat subduction by the mesoscale ocean eddies. So yeah, we have both vectors, and then we have this pretty realistic pattern. Yeah.
Hi, Sarah.
Hey.
Thank you. You showed this kind of amazing swath of research using a lot of different forcing experiments. So this is kind of related to Paul's question. You have aerosol forcing, surface forcings, solar forcing, CO2 forcings. Do you have any comments on kind of, are all of these kind of all equal, or some of the different forcings better suited for different tasks? Like if you were just going to choose one, what would you choose? What do you think is best?
Yeah, I think depends on the question, but I think it is not explored whether the long wave forcing and the short wave forcing would have really the same impact. So actually we're planning aquaplanet simulation, doing this banded experiments. Here we only use our surface forcing, and we're planning on doing the CO2 forcing with banded. And maybe, I'm interested in whether long wave and short wave forcing would be different. Yeah.
I also have a question for you. So everything is so interesting, and you have many modeling work. And so my question is that, can you try to, or have you tried to find some signal or similar thing in observation, like the temperature, like a lead lag between the, or like the Southern Ocean temperature signal, lead some signal in because we know in the real world the ENSO is always there, and is the most energetic driver. Global climate, right? So it's always the most energetic thing, right? And or what type of data you need if you really want to find this type of like the polar-driven signal in the tropics.
In observations, I'm actually not sure. I personally haven't looked into observation itself for this linkage between the extratropics and tropics. But I think Aaron Donahoe at University of Washington might have looked at it. I think he looked at that we can identify this connection in the AMO signature. So only for the long enough, the response with long enough frequency period that you can observe this connection between the extratropics and tropics. So if the extratropical mode is too high frequency, then it's actually going to be obscured by other stuff, and then you won't be able to find any signature in the tropics. So you need actually a pretty stable, low frequency extratropical perturbations, and then I think you can filter out the tropical component that is associated with that perturbation in the extratropics.
Thank you.
Hi, thanks, Sarah. That was super illuminating. My question, I must admit, is a bit naive to, this is potentially just completely unfeasible from like a modeling perspective, but I was interested when you were talking about the figures that are up here right now about the difference between what is driven by the resolution of the ocean field versus the cloud feedbacks. Is it possible to essentially run a version of this model where the ocean resolution is coarsened, but you still somehow retain the same mechanisms and the same processes that you have in your atmospheric model to try and separate out the contributions of the signal from the cloud feedbacks and the mesoscale eddies?
Yeah, so at the Institute, we are planning on smoothing out the ocean resolution in this particular high resolution. But I think it's going to take time.
Yeah. Cool, thanks.
Yeah.
Thank you for the great talk. And I'm curious about what about the ITCG bias in icon simulation, because you mentioned that the ITCG bias is also important to
that's actually a really good question. So in this icon, so of course, this icon is not perfect. Actually, there is a strong precipitation bias in the mean state. Actually, so here it's pretty dry. There's very little precipitation in the wormhole region, and that is a reason actually why this cooling signal extends all the way into the maritime continents. Yeah.
Does that ITCG bias is related to the atmospheric resolution or other?
I don't know. Yeah.
Thank you.
Yeah.
Thanks, sir. All right, so I want to build off of what Chingwa was asking about, like kind of the ENSO, and so I get that. You know, an ENSO response makes sense because there's a lot of, I guess, energy in the system. But it seems like a lot of ways when we shake our models, force them, you get this ENSO response a lot. It's like a preferred mode. And so does that concern you that our models are just like, do we like build our models to reproduce an ENSO because that's the biggest signal that we see? You know, so, or, you know, should we expect the system any way we hit it to always produce an ENSO-like response?
Yeah. So in this icon simulation, there's basically no ENSO. The ENSO signal is too weak. So we're actually debating ourselves. Is it really critical to have ENSO for understanding the long-term trend? I want to know your opinion about it. Yeah.
Thank you very much.
Thank you.
Yeah, let's move on to the